Okay, let me start the class. Today is week number 2. So I posted class schedule. Is this schedule? Means schedule can be changed anytime, right? Depending on the progress. So especially for me, this is first time to teach linear algebra. So I really don't know actually how fast, how slowly you're going to move. So I'm going to adjust the schedule, okay? So this schedule. Then we have 15-week class, but we're going to come up with some makeup class for Korean Thanksgiving and whatever holidays we have. On this column, right? On this column, we're going to, let's say, why we don't have this? Okay. Then we have here all the homework due date, right? Jiyoung-tak, we have 10 homeworks, right? This is plan also as well, so we can change that. But so one way to learn about this linear algebra, sometimes it's better to solve for yourself. Then you can really understand. You can really just make your own. So this is currently my plan. So today, actually, I'm going to discuss about elimination with matrix. Probably most of you learned in high school. Okay, so first 2 weeks actually is pretty easy. Okay, let's move on to this slide. So I'm going to try several formats. This one also, actually, I just prepared this slide using my handwriting. So next time, actually, I try to start from scratch using digital project. I'm going to just handwrite on paper, then I can project. So I'm going to try something else. So small. Okay, today I'm going to review last week's lecture. Then for this week, today and tomorrow, I'm going to discuss 3 topics. One is elimination with the matrix, also matrix multiplication, and inverse, also factorization. So whenever you have a question, just raise your hand. You can ask me a question in English or in Korean. Okay? So review last week. In the first class, I mentioned about modeling and solving. So linear algebra actually is problem solving, right? But in reality, you have to model the problem. You have to define the problem, then solve it, right? So I gave some examples, whatever these balance levels, right? There's so many other examples. You have made some circuit theories, all other areas. So one is just from real system to abstract model, this modeling area. So you can model with some linear systems. Here means linear system means just n equations and unknowns. Or Jiyoung-tak, for certain problem, you may model differently. In high school and also in college, you are learning calculus, right? Differentiation and integral. Also differentiation integral might be used to model certain area. Can you give me some examples when you utilize differentiation or integral? Okay. And also some other topics like differentiation. Like when you velocity, right? From velocity, let's say you can compute what's the distance traveled for a certain time, right? That's most like integral velocity, like integral v dt becomes distance, right? Also from v, when you differentiate dv dt means what? Acceleration, right? So in that case, we are using integrals and differentials, all those things, right? So most of the mathematics. We do not learn mathematics simply for fun. I don't know, for some people, 이상욱, math may be fun. But we are engineer, so we are using mathematics to solve a problem. So in this case, actually, we assume whatever model we have, systems, we can model well using linear equations. This is most simplistic model, okay, linear model. More complex model is you can have some quadratic, like squares, or integrals, or exponentials, or log, lots of other complicated formulas. But this one is simplistic model, okay? So, but we are modeling as a linear equation, n equations with n unknowns. But when you say, I mentioned one example about velocity and distance, right? When you model that with this linear system, it doesn't make sense, right? So whenever we apply this, we have to find whether it's good model or not. Also, in modeling, then we have some kind of errors introduced. I mentioned that when you model, you have to measure perfectly all the parameters. There's errors in estimating parameters. Also, when you represent the computer, there's another problems in accuracy problems, right? Computer is not infinitely accurate. Computer representation of number is always approximation. So when you compute, then you have problem, right? So that's the modeling part. The other one is once you have a model, then we try to solve it. For linear equation, 양승호, you already know how to solve that. You learned in high school, right? 속업 of Gauss elimination, right? But when you try to solve the problem, most cases you have one unique solution. But in some cases, you don't have any solutions. Like two lines in parallel, they never meet, right? Here is actually simplest example, two lines, they cross, there's one intersection, right? Two lines may be parallel, there's no solution. Another one is many solutions. It's almost infinite solutions. Two lines are coincide, right? So most problems like this. So we know how to solve them. During process of solving, we know, okay, there's no solution, the infinite solution. Or even solution, because we are using computer, not hand, right? In that case, also you have some accuracy problems, right? Computational errors build up, like when you calculate, right? Round off, right? So sometimes they may give very funny answers. In reality, when you use computer, they only provide approximate solution, right? Sometimes, Kim Young-jin, you are expecting approximate, but sometimes they provide very funny solution. So that's the things you can learn about later. Okay. So these are things you already know, so I don't have to explain, right? Just solving linear equations. So even in this area, you know there are just one way to represent one as a linear equation. Another way, more neat way to represent it as a matrix and vectors, right? So one is coefficient vector, right? 2 minus 1, this coefficient. Then xy, then multiple xy is vector, then this b vector, right? They call axb. So I'll just move very fast, right? Everyone knows these things, right? Then there's two ways to represent. One is raw picture. In this case, just we somehow show each equation one by one. Okay, so this one you know that, right? Second one, in this case, actually, we represent a little bit differently. In this case, actually, we are representing column by column. We represent column as a vector. Okay, so 3 by 3 matrix, I says there's 3 vectors. They are combined using this xyz as a parameter, just a linear combination. Okay? So when the b vector, we know how to solve them. Sometimes, here I said there's no solution, sometimes too many solutions, right? The vector space. I just checked the 수학의 정석. This is 공간, space, right? So Kim Won-jun, can you explain what's a space?
It's an empty volume.
Yeah?
Empty volume.
Volume. I'm saying in this context, okay, space in this vector space. What is vector space? So anybody can explain? Yebin, what's a vector space? Have you learned in high school or not? Just 고등학교 때 배웠어요, 안 배웠어요? In high school. Space. You know, this is X, Y, G, right? Any point in this space, this is three-dimensional space, right? Somebody says, oh, this is three-dimensional space. Here you can say this is whatever, A, B, C, right? So, or you can say, okay, this one is called, you can say this X vector, you can say this Y vector, you can say it's G vector, right? Okay, assuming this one is just unit is 1. So that means it's A, B, C, whatever, what's the vector of this? This one is somehow A, X vector, right? Plus B, Y vector, C, G vector, right? That's the way you can represent this point, right? Assuming you have all values of A, B, C, all the combination of values, then you can represent all the points, right? Whole space, right? There's a whole space, right? So that's what really it means. But assuming, then how about the AX plus BY only? Does it cover whole space or what? Just one plane, right? One plane. Then AX, obviously here I say it's all A for all B, right? Then I say AX, just represent only one line. But it's, then oh, I have more. Then I say whatever this DW, right? This four-dimensional space, right? Now four-dimensional, two-dimensional space, even here it's just AC, just one-dimensional space. What is zero-dimensional space, Kim Myung-jin? Just one point here. Okay, so it's concept is very simple. Because most of concept in mathematics is very simple. 박한서, why? Concept should be simple, otherwise there is no use, right? So, like suppose Lee Young-kyung defined concepts which are very, very difficult to understand, then nobody will use it, right? So why do you introduce concept? Because even simple, then we introduce concept, then everybody has the same understanding. That's why we try to define such a concept very formally to help everybody to understand common understanding, okay? Then we know what it is also all those issues I think you 직교 in high school, right? Probably you learning here just English terminology for the whatever Korean terminology you learned in high school already. Then okay, today's new topic is elimination with matrix. So last week, this is linear equations on top, right? This is linear equation. Why it doesn't work that well? Okay, this is linear equation on top. then its bottom up, this is matrix representation, right? So rather than solving this, we want to solve in these matrix forms. 지영자, have you learned this solving this elimination using matrix forms in high school? No? But when I see the 수학의 정서, they have concept of inverse of matrix and transpose. All those things you learned, right? You learned just equal, right? Same, just same, it's the same. What's the difference, right? Because you don't learn 100 dimension, whatever. Just once you learn the second degree, then two-dimensional, then just extension. Okay? So, you already learned this elimination in equation, right? Now you are just learning in elimination in matrix. Why do you learn? Why do you do in elimination in matrix, not in equation? Yeah? Yeah, it's much more convenient, right? But concept is same. Concept is same, basically. So you all know that, right? So what you do here is, this is original matrix. Then we try to remove this one, right? Then multiply 3, then you know how to make this, right? So anybody has any questions to how to just convert from this and that? Kim Jong-un, do you need any explanation or just it's obvious, just let's skip it? So what do you want? Yes, we try to make some this diagonal. Because this one is triangular matrix. Triangle is 삼각형, right? This upper triangular matrix. We try to make this, then we can solve the problem. Okay? 박한솔, do you agree with that or not? So this is original matrix. When we convert to this matrix, now I know how to solve it. This just 박창호. This is another representation of linear equation, right? That's what we discussed about. Oh, it is. Oh, no, not this. This is what it did, right? This is just a linear equation. This is the way you're going to convert this, right? Then from here, now I know how to get value of g. From there, then I can substitute here, then I know how to get the values of y, then out these things, right? From here, it's not that obvious, right? So having some transformation, basically, like this 4 times this first equation, then subtract from this, then this will be just converted, right? This is what we are doing, right? So basically, we can do the same thing. That instead of using these equations, we can have some matrix forms. So that's all we do here, actually. Then once we get this, now it's a 지영탑. Problem is almost solved, right? We can come to G, then from back substitution, we can solve Y, then we can solve X, right? So all the difference is just we use here just matrix forms. Right? Matrix forms. So, yes. This one? Can you guess? right? This is using this one, right? So from this, let's say, what is 2 stand for? Row 2. What is row 1? Using row 1, okay, using row 1, we try to convert row 2, then try to make this one to 0, basically eliminating whatever coefficient for first parameters. So this is using, this one is now is between 3 and 2. Okay, once you have this, then using these two equations, this is a matrix, now we try to move this. So what operation should we do this? 양승호, what operation we do this to make this thing happen?
Sorry, I have no idea.
고지훈. I said just this is using some transformation. So what kind of operation do we do this? Here. What it does is like subtract 3 times row 1 from row 3, right? No, row 2, right? 양승훈, now can you have idea how to make that? Okay, that's what you. So from here to here, what do you do? What do we do? Here's subtract, right? Also the same thing, right? Subtract the row 2, right? How many times? 2 times row 2 from row 3, right? So actually, this just review of what we learned in high school, right? So by doing the transformation, now when you have a sequence transformation, now regular matrix A becomes upper triangular matrix. Okay? Yes.
그럼 만약에 저기 두 번째에서 세 번째 넘어가면요. 두 번째 그러니까 마지막 거에 0, 2, 마이너스 2 남았어야 되나요?
네? This one? Oh, sorry. Yeah. Thank you. Thank you. Okay, thank you. How can I fix it? Let's fix this. Let's say, how should I do this? Oh, no, not this. Right? Okay. So we just call, whenever you do this, we just call somehow it isn't there. This one is we just call pivot. Like, what happens? This value is 0. Do you need this computation? Somehow, let's try this. Somehow, when you do this, somehow this one color doesn't appear there. Somehow it says this computation How about when you have a 0 instead of 2? 김상, what are you going to do? 이민수, what are you going to do? Because once you have a 0 and minus 2, then there is no way to progress anymore, right? So Himyo-chan, what are you going to just stop there? Just exchange low, right? So we all know that, right? Once exchange low, right? Then we can solve a problem, right? Then, so when you have such a problem, we're going to temporarily we are failing it. By switching low, then we can just continue, right? What happens is you cannot find any row to replace. For example, oh, this is row 0 again. Then what are you going to do? So there is no row to switch, right? In that case, you failed. It means you may not have any unique solution. Okay? You may have infinitely many solutions or no solution. Okay, depend on the B vectors. Okay? So just rather than simply following this process, so each step you try to understand what really it means for each case. Okay? So that's the way you have to understand that, right? Okay. But up to now, we only use just A vectors, right? Just coefficient vectors, right? Real to solve the problem, you have to just augment B vectors. Just here, vector actually, this is whatever AXB, this is just B vector. I just added as a new column. Just this dotted line. Just presume this is almost 3/4 vectors. Then just apply the same thing. Okay? Then we can compute both. Then actually when transform this, then actually this equation now becomes this. From here, we can just solve the problem, right? So AXB, AX equal B, just be transformed UX equals C. Then using back substitution, we can solve the problem. Okay, so most cases you just use this the way to solve the problem. Okay? Yes. It's the same thing. But this is another way to represent. So you can understand more easily. Whether you just maintain a separate matrix or not, it doesn't matter actually that much. So end results are same, but just this is more or less, now rather than, matrix operation, then vector operation. Now, okay, there's just a little bigger matrix, just we have just operation just once, okay? What is identity matrix? Hyung-ta, what's the identity? I don't know. It's in high school. You learn the identity, but what's the Korean translation of identity? I don't know. 항등? I don't know. 예? 단위? Okay. Just because we know the scalar operation, right? A times this one, right? This is unit, right? Then A times we call this one is inverse, right? In matrix, you may say, oh, this is scalar operation. I can do the same thing. Just what the hell? Instead of 1, we have I. Then what's the representation of I? Means, oh, this is a matrix. All the diagonals is 1, or the area is just 0. For 4 by 4 matrix. So basically, it's just almost identical, right? Yes, in that case, oh, this is all same, also A, right? Yes, oh, then should be right. So basically, then I say this. What is A times 1 in scalar? A, right? A, right? Then I say A, whatever, right? A, then I say, oh, I know this is 1, right? Except A is 0. In the case of A is 0, I have no idea, right? Just all the values, right? Then same thing, here is, oh, A, whatever, I don't know. This is A. What's this? This is called, we just, same thing, I, with all the diagonals 1, other 0, is called, this one is identity matrix. Okay? So, if you don't trust me, then you can try it out, right? Just diagonals 1 and 1 that you can compute. Somehow here is on this slide, right, on screen, the question mark just shows in red, but somehow in my computer it's just same color, somehow strange. I need to find out. Okay. Then another question I'm asking you, this is original matrix, right? Then using this row operation, I come up with this one. Somehow, can you come up with this transformation by multiplying another matrix in left side? Let's put it this way. Let's say I times A is A, right? Yeah, we know that, right? But here is somehow we come up with this is matrix A, this transformed matrix, whatever another A prime. Can you come up with some matrix by just multiplying them? We're going to have that value. 이선태, can you come up with any matrix? These matrices somehow represent this operation. Right? Somehow that operation, right? When you say 1, 1, 1 diagonal I matrix, same, right? But for only second row, second row, this one? Yeah. Somehow, like when you say it's 1, 1, 1, then just same value, right? How about when you say, what about this question mark here, when I say, does this work? Can you explain why it should work that way? Because one thing is just purely just or right or wrong. It's not that important, right? You have to be able to explain them, right?
쟤랑 -3이랑 첫 번째 줄에 있는 놈들이랑 하고 1이랑 두 번째 줄에 있는 놈들이랑.
So then just I'll show some more pages. Then it's obvious, right? We just call it. This is matrix A. This is elimination matrix E21. That's the way we just name it. This is -3. Okay. So all the diagonals, all you want is all difference because subtract 3 times row 1 from row 2. That's why we just put it here. Okay? When you say subtract 5 times row 1, then it should be -5, right? Okay? Then why? Yes, you can multiply that. Then also you can represent a little bit differently. So this is more or less another way to view that. This is okay. This is row vector. From row vector, this is the 1. Then what really means -1, 1, 0 means this is more or less -3 times row 1 plus 1 times row 2. Then whatever this 0 times row 3. This is more or less combine those things well, right? So this is what really it means. From row 2, subtract 3 times row 1, right? That's why. That's why that corresponds to this, right? So you have to visualize them. From that, okay, I can do anything now. Okay. So this is another case, right? Another case you can draw these diagrams as well. Then one step, then second step, then the other one we have here, right? Then 2 steps now is another one we can draw, right? So from previous one result was E21 times A. So by multiplying them, basically what we do is actually here actually initially we have A, okay, then we multiply whatever E21 had some intermediate result is this one, right? Then another operation for between row 2 and 3. Now it's E32. Okay, what he got was U, right? So basically, when you say this is the 1, also this one is can you represent this one is are they identical or not? Because this is multiplication, right? You can change the order. Still is the value same thing, right? That's why we call just this E matrix. Okay. So basically, we do whatever these row operations, subtract all those things, but actually you can represent as a matrix. Okay, so basically here actually what you do was, okay, actually initially we have A, just applying here, using whatever E, then A, then we have just U. So applying this E operation, whatever these row operations, we can make triangular matrix. Okay, this is really is elimination. Then from that, you can solve the problem. Any question up to now? This is actually the same thing what you learned in high school. You just learned in using linear equations. we just representing them using matrix forms. But actually principles are exactly the same. Okay? But in this case, you don't have to explain in English, right? Using this elimination matrix, you know what to do. Right? Okay. The other one is up to now, actually, just we try to remove certain entries, right? Can you switch like rows? Like whenever you hit 0, right? Then in pivot, you have problems in progressing, right? So in that case, you have to switch row, right? Can you represent switching row in matrix forms? Basically here, original matrix A, B, and C, D, right? Somehow, by multiplying some matrix, certain matrix, now actually this row, oh, this is too sensitive. Here actually we are changing the row, right? AB becomes second row. CD becomes first row, right? So can you come out with some matrix here? 0, 1, 1, 0, right? So that's most permutation matrix. Okay? So columns you can do, but actually this is not useful, but this is pretty useful, right? So you can represent it, permutation also as a matrix. It means all the operation you have is whatever E2, E1 is more the elimination matrix. Now here somewhere you say, oh, I'm going to exchange that like E32, whatever you have. Okay, now I'm going to say whatever P3, I don't know, is 32, then whatever E21, whatever. Right? This more P is permutation matrix, right? So basically all of the operation we have in Gauss elimination, you can represent as a multiplication of either elimination matrix or permutation matrix. When you multiply all of them one by one, that's a whole elimination matrix. Okay? Okay, what else do we have here? Up to now, actually, we computed, we have A, right? Our goal was to diagonalize A using whatever row operation, substitution or permutation, right? Whatever elimination, right? So all those operations we represent as a matrix. Multiplying them, we got U. How can you recover A from U? Let's say this is row operation, right? What's the inverse of this? Well, it means just recover. Whatever you did, you try to recover. 시영탑. What's that? What's the meaning of this first one? Okay. Subtracts 3 times of row 1 from row 2, right? What's the inverse of that operation in English? 이혜빈, what's the inverse of that operation in English? Add 3 times of row 1 to row 2, right? Right? Because before we just subtract 3 times row 1 from row 2, right? That's add, right? Whatever you subtracted, right? Then can you represent that as a matrix? Instead of minus 3, now it's plus 3, right? 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 It's multiplied, right? This is now plus 3, right? So you have to understand that, right? Now is this more or less, once you subtract, then add, then just when you multiply them, just you are recovering, right? So it means whatever the next one is, both has an inverse relationship. When you multiply both matrices, now it should be identity, right? Okay, I got to discover about the matrix multiplication. So, Park Chang-ho, do you know how to multiply matrix? You learned in high school, right? So, I just assume you understand how to multiply matrix. So here actually I do not teach how to multiply matrix, but I try to view this multiplication from different angle, okay? Rather than teaching you how to multiply matrix, okay? Oh, this is the way I can see it. Oh, this is another view to see this multiplication. Oh, this is some other views to multiplication, okay? So from each view, you can get some insight. Okay? Please. This is matrix multiplication. You understand. This is what you learned from high school. You know how to multiply vectors, right? Especially 내적, inner product, right? Right? This is more or less like matrix. Then you can see this matrix multiplication as a, okay, each row vector at A, each column vector B, then multiply as an inner product. Okay, that's the way you see it. So that's the way you can find each entry. So in order to get, let's say, C2, 5, that is row 2 times column whatever 5 as an inner product, right? Then there's the first one is just representation as inner product. Then you can just expand them as just summation forms, right? From here, actually, in order to provide the multiplication, there's certain conditions or dimensions should be satisfied, right? Just number of columns in A, number of rows in B should be identical, right? Otherwise, you cannot multiply. Say vectors of 3 entries, vectors 5 entries, when you come out with inner product, it doesn't work, right? In order to make inner product, their dimensions should be identical, right? So it's very simple. But this is the way you learned in high school. Okay. Actually, this is another way. This is more or less a little bit differently. So here, actually, I see each column of C, I can see as A times column vector of B. Yu-Hyung, can you understand this? Like first column of C, right? C1 is A times first column vector of B1, right? Then second column is A times second column vector of B, right? Then here I say columns of C are linear combination of column A. Okay, let me put it this way. So let's go back to what's a linear combination. First of all, let's just go back to what's the linear combination of vector. Let's say x, y, and g. Well, let's assume x, you may say 1, 0, 0. Y hat is 0, 1, 0. G hat is 0, 0, 1, right? This is more or less unit vector. This is x hat, y hat, this is g hat, right? Okay. Then, what's this point? I say this is A, B, C. So how can I represent this? This is more or less, oh, that's easy. This is more or less, this point is x hat, y hat, c, g hat, right? This is, I say, is linear combination of three vectors. Okay? So how can I represent this as a matrix? Can I represent this as more or less here actually x hat, y hat, g hat. This is more or less representing as just an equation, right? This is another way to represent, right? So picture same thing. When you multiply these things, actually, this is what we are getting this. A, B, right? So this is another way to view. So this is another way when you see this multiplication. Oh, first column of C, bad. Like first column of C is somehow multiplication of matrix A, then column 1, right? So this is the way you can represent. Assuming this one is actually, so everyone is column vector. Okay, let me try to explain this. Here's whatever vector, matrix. Okay? Then you have all these elements here, right? Assuming this one actually size n by n. Okay? This is, okay, this is a matrix. I know that, right? Some people says, oh, let's see this S, O. Can I see this one as somehow? Somehow, oh, let's assume this is A, right? Can I see this as more or less A1, A2, can I see as each column as a separate vector? What's the dimension of this vector? M, right? Number of rows, right? This is one way you can see. In that case, I just call this as a column vector. Okay? This matrix, you can see, oh, this is collection of column vectors, right? That's something, oh, that's more than that. I'd rather see it. This is the way I like to see it. Right? You can say there's a row vectors. Each row vector, you know how many of them, right? Also, what's the dimensions of vectors, right? So basically, even when you use matrix multiplication, using this concept, that's the way you can see it. Somehow, actually, when you have multiplication of vectors matrix, when you read many books, they try to explain them as in geometry. 기하학, right? Even when you have inner product, what is length, then there is what's the angle between two vectors, right? This is more or less geometry interpretation, right? So think about it. So, okay, so this is another way to see it. Yeah? Same thing, you are viewing different angles. Okay. Then why do I do these things? Here it says columns of C are the linear combination of columns of A, right? For example, when I say each vector here, right? I say, oh, actually, it's a vector. Is one of the actually vector is not. One of the vector here actually. Instead of this, when you combine them, because when you each vector is independent, they span whole space. When you do that, actually, these two vectors are dependent, right? Then when you combine them, whatever the space are covered by the linear combination does not span whole space or limited space. But so that's the way you can just conjecture them, you can explain them, right? When you use just pure matrix forms, you are not able to explain them. So when you have concept notion of vectors, now you can explain them. Okay? That's why sometimes I see as a matrix, sometimes I see as a collection of column vectors, so other times I see as a collection of row vectors. The same thing, just depending on, just for your own convenience, right? So that's the way we approach them. This is just what is complementary view. Okay, instead of columns, now rows. Okay, this is another way. So I'm going to skip them. Okay, last one I'm going to discuss about this block matrix multiplication. Up to now, most of the examples we are discussing is just say 3 by 3 or 4 by 4. Most cases for explanation just use 2 by 2 or 3 by 3, right? And some computation in real engineering computation, sometimes you have to deal with hundred by hundred matrix. It's a big matrix actually. So sometimes you have to deal with like image processing problems. It's more than that. Like for example, Kimijo, you have phone, right? So how many pixels do you have on your phone camera? Hmm? 2 megapixels or whatever, right? Phone camera, you have some cameras, right? So Bakansol, how many pixels do you have on your phone? 5 million, right? When you represent each of them, let's say sometimes like 124 is a 1 megapixel camera, right? Right? So it means the matrix is 1024, 1024. So you have to compute in many cases. So in image processing, they do lots of computation. Or from image processing, from there I try to make picture more clear. Sometimes I just make whatever, remove noise. Then in that case, you have to deal with this one. 5 megapixel, much bigger, right? So in that case, then there's lots of multiplication. Also, many cases actually even this big matrix. Sometimes many cases actually many of them are zero. Lots of the values, many of them are zero. They call it sparse matrix. What's sparse? Not dense, right? A sparse matrix. So only few percentage of the entries are non-zero, others are zero. So in that case, we try to optimize computation. Okay? So one way to, with big matrix, when you multiply them, oh, your matrix too big. Can I somehow divide this matrix? Like, oh, this 1024, 1024. Can I divide them? Because just multiplying two big matrices is too much. Then I just divide it half. Yeah, A1, A2, A3, A4. Then when you multiply them, then you more or less, okay, the C1 is, okay, this is the way. C1 is A1 times B1 plus A2 times B3, whatever. So this, sometimes certain blocks are completely zero. Then you don't have to compute. So lots of tricks are used to just make matrix multiplication more convenient and efficient. 오케이. 오늘 강의는 이걸 끝내고요. 지금까지 해가지고 질문 좀 받을게요.
저 각각 하나가 다 행렬인 거죠?
네. The sub matrix. 그러니까 1024면 512 by 512. 그럼 4개가 나오죠. 그죠? 그렇게 해서 따로 계산하면 될 수도 있지. 또 뭐 다른 질문 있어요? 예.
아까 그 엘리미네이션 도대체 3행에서 2행으로 빼고 엘리미네이션은 왜 하는 거죠?
예? 엘리미네이션? 언제 할 적에?
아까 3행에서 서브 로우에서 세 번째 로우를 빼고
그래야 문제 풀리는 거 아니에요? 하이스쿨 때 배우지 않았어요? 그러니까 그 트라이앵글러를 이렇게 하면은 그다음부터 문제 풀 수 있는 거 아니에요, 그죠? 그렇게 지금 만들기 위해서 하는 거지. 그러니까 지금 만약에 이게 이제 사실 뭐 비주얼라이저도 똑같은 거 아니에요? 이게 이제 원래 이렇게 지금 A란 게 있잖아요, 그죠? 이게 저 코에피션트 매트리스거든. 그럼 여기 주사 있잖아요, 그죠? 이걸 궁극적으로 목적이 뭐냐? 일단 푸는 거는 이 목적을 다이아고널만 이렇게 있고 위에도 뭔가 있는데 여기는 5를 제로를 만들면은 여기서 또 요거 값 내서 그다음에 여기 대입해서 요거 값 내서 대입해서 두 개 하면 이렇게 풀 수 있잖아요, 그죠? 무슨 말인지 알겠죠, 그죠? 그래서 이걸 하기 위해서 여기 있는 엘리먼트를 전부 제로로 만들어야 되거든. 예? 제로 만드니까 여기서 봐갖고 요거 제로 만들려면 여기 보고 여기 숫자 봐서 계산해서 빼서 영어로 만들고 그것도 더 바뀌고 이런 식으로 하는 거지. 예? 그걸 오늘 설명한 거는 그걸 이퀘이션에서 안 하고 그냥 매트릭스로 한 거고 그때 단계마다 하는 게 이런 작업을 말로 해서 했는데 이게 봤더니 완전히 이상한 뭐 매트릭스 뭐 이렇게 뭐 E32 뭐 이렇게 매트릭스 이렇게 멀티플라이 하는 거네. 결국 이렇게 하는 거네. 각각은 요런 경우는 이렇게 하고 요런 경우는 이렇게 하는 거네. 근데 이제 갖다 퍼뮤테이션 로로 바꾸면은 또 다른 식으로 P 같은 게 있네. 그래서 이런 걸 해서 이거 멀티플라이로 하면은 이게 되네. 그래서 사실 여러분들이 리니어 이퀘이션을 풀면서 알고 하던 거를 매트리스 표현하면 이렇게 되는 거고 이 매트리스 발견해서 이런 식으로 컴퓨테이션 하는 거지. 또 다른 질문 있어요? 사실 어떤 면에서는 똑같은 거 하는 건데 그냥 매트리스 형태로 하는 거예요. 예? 그냥 매트릭스 형태로 저 매트리스가 정해지면 어떤 매트릭스 이런 데 도움이 되더라고요. 스페셜 매트릭스도 있고 여러 가지 개념을 갖고 여러 가지 얘기를 하는 거죠. 예? 다른 질문 있어요? 예. 꼭 그럴 필요는 없지. 근데 이제 어떤 컨디션이 맞아야지. 어떤 컨디션이. 왜냐면 이게 이제 여기서 할 때는 이게 n 곱하기 근데 요것도 A1, B1이 계산이 가능하려면 렉터하고 상관이 없죠. A1, B1에 뭐하고 뭐가 같아야 되잖아요. 그죠? 각각의 그 컨디션이 맞아야지. 그렇지. 그러니까 똑같이 적을 필요는 없고 이게 있잖아. 지금 이제 가운데 쪼갰는데 뭘 가운데 쪼갭니까? 아니면 뭐 여러 개를 쪼개도 되고? 그지? 9개 쪼개도 되고. 나는 이렇게 쪼갤 수도 있지, 그지? 야, 좀 더 쪼개. 그럴 수도 있고, 그지? 그렇잖아. 아니면 왜 이렇게 양쪽이 똑같아? 여기는 하나 쪼개고 여기는 많이 쪼갤 수도 있지, 그지?
저거 예를 들어서 4 곱하기 4행렬이 곱이면 이걸 2 곱하기 2로 바꿔서 여기서 한다는 얘기예요?
그렇지. 그러니까 예를 들면 이제 현재 같은 경우는 그냥 나는 아유 한꺼번에 숫자 많은 거 소화 못해. 그러면 이제 요거 계산해 놓고 요거 계산해 놓고 따로 계산을 하면 되지, 그지? 그런 거지 뭐. 이제 많은 경우에 이제 만약에 이건 뭐 어떤 모여가 무슨 제로다 하면 이제 그 다음부터 계산이 훨씬 더 심플해지지. 그 스페셜 매트릭스에 있으니까. 또 다른 질문 있어요? 예.
역행렬 구하는 거 좀 특이한 케이스여서 그거 쉽게.
현재는 역행렬 구하는 거 아직 안 배웠어. 아까는 이제 그 엘리미네이션을 하는데 뭐 원위치 이렇게 하는 거죠, 이제. 근데 원위치 하는 게 사실 그거의 엘리미네이션 매트릭스의 원위치가 그거의 역행렬이잖아요, 그지? 근데 여기 현재는 A의 제너럴 A의 역행렬 하는 건 아직 얘기 안 했지, 그지? 아직 안 했지, 그지? 그래서 여기서 이제 E2, 1 이런 게 있으면 요거의 역행렬은 보니까 뭐 로 1에 곱하기 3에서 로 2에서 빼라. 그걸 거꾸로 계산하면 더 하라. 그러면 쉽잖아, 그지? 네? 그럼 개념적으로 쉽게 그냥 계산이 아니라 개념적으로 쉽게 만들 수 있는 거지, 그지? 무슨 얘기인지 알겠죠, 그죠? 이제 그런 거 같죠. 근데 퍼뮤테이션은 한 번 바뀐 거 또 바꾸면 되잖아, 그죠? 그러니까 퍼뮤테이션은 예를 들면 P2안에 인버스는 P2안 아닌가? 스위치에다 또 한 번 스위치하면 되잖아, 그지? 지영장이 그런 거 아니냐? 스위치에다 또 한 번 스위치하면 되잖아. 야, 너랑 나 선물 바꿨다. 야, 또 바꿔라. 뭐 이런 원시 되잖아, 그지? 그래서 여기서는 여러분들이 그냥 저 포뮬러가 중요한 게 아니라 포뮬러에 대한 언더스탠딩을 해야 돼. 그냥 수학 문제만 푸는 게 중요한 게 아니고 왜 저런 거 해야지 그걸 여러분들이 실제로 활용할 수 있는 거거든. 그냥 블라인들리 외우는 거는 전혀 의미가 없어요. 그렇잖아, 그지? 우리 써먹으려고 하는 거지, 그지? 오케이? 오케이, 강의는 이걸로 끝낼게요. 수고 많았어요.